From today, we are going to start a series of the statistical analysis, which are known as ANOVA, or the analysis of variance. So the ANOVA, or the analysis of variance, is a very famous kind of the statistical analysis that is widely used in research, in biology, in medicine, in agriculture, or social sciences, and in different fields. So this test is basically used for the comparison of the mean values between samples. But in this case, this is used for the comparison of mean values between samples which are more than 2. So if we have the 2 samples for which we want to have the comparison of their mean values, then we apply the t-test. But if we have the number of samples more than 2, if we have 3 or more number of samples that we want to compare the mean values of, then we apply the ANOVA, which is the analysis of variance. Now, to understand the concept of ANOVA, we want to understand the concept of multiple testing, right? So sometimes we need to compare the values of more than 2 groups or more than 2 samples. For example, the length measurements of 3 races of a species living on 3 different islands, A, B, and C. So in this case, what we have is we have the length measurements from 3 different locations. So we have the race A, which is present on island A, we have the race B, which inhabits the island B, and we have race C, which is present on island C. And what we have calculated, or what we have recorded from different individuals of this race, we have recorded their length measurements. And now we want to have the comparison of their mean values, that if their mean values are similar or if their mean values are different. So what is the test that we use for the comparison of the mean values? We use the t-test, right? These are the independent samples, so we are going to use the student t-test. But how we are going to apply the t-test here? Because the t-test can only incorporate 2 samples. So the t-test, it allows the comparison of only 2 samples, but now we have 3 samples. So what we are going to do? We are going to do multiple tests. So in this case, we are going to perform 3 t-tests. The comparison of A and B samples, the comparison of A and C samples, and the comparison of B and C samples. Because t-test allows the comparison of only 2 samples at a time, so that is why we have to perform 3 t-tests if we have 3 samples, right? Now, does it look laborious or time-consuming? It doesn't quite look so, because these are only 3 t-tests that you're going to perform, right? But if you have to compare 7 samples, then what you're going to do? In the previous example, we had only 3 samples that we wanted to test. But here we have 7 samples that need to be compared with each other for their mean values. So how many tests are you going to do? You need 21 t-tests to compare all possible pairs of means, because the possible number of the pairs of means are 21. So you have to perform 21 t-tests. So this seems to be quite a Herculean task. This is very laborious. So this seems to be very laborious because you have to perform 21 t-tests for a single experiment. But we always have some champions who are always ready to do these kind of the huge tasks. So even if someone agrees, even if someone is a champion, and if someone agrees to do these 21 tests, the statistics is stopping you. So there is a statistical objection to do these kind of multiple testing. And what is that statistical objection? That statistical objection is based on chances of making type 1 error, because multiple testing causes, or it increases the chances of making a type 1 error. Now, what is a type 1 error? Type 1 error is a false positive result. So false positive result means that you are rejecting null hypothesis when it should be accepted. So what we are talking about here, we are rejecting null hypothesis when it should have been accepted. So when does this happen? So in multiple comparisons, which are used to test the null hypothesis that means of several populations are equal, right? So What is the statistical test for? The statistical test is to check the null hypothesis to be true or false, right? So if you are going to perform a single t-test, right, if you're going to perform a single statistical test, so what is your desired level of significance? Your desired level of significance is 0.05, right? And if you're going to do multiple tests, then you have 0.05 for each of these tests. So the level of significance is 5% for each of these comparisons, which means that there could be one wrong conclusion expected for every 20 tests. So if you're going to perform 20 tests in a single experiment, then there is a chance that one of those conclusions is wrong, right? Why? Because the inherent error rate for every statistical test is 5%, because you are accepting or rejecting null hypothesis at the probability level of 0.05. So this means that probability of accepting null hypothesis is less than 5% and probability of rejecting null hypothesis is more than 95%. But still there is a 5% chance, because you're deciding this at 0.05 level of significance. It means that there is still 5% chance that you're making an error. There is 5% chance that your null hypothesis is actually true, so you have to accept the null hypothesis. So the inherent error rate in every statistical test is 5%, right? So it is maximum 5%. So it means that there is 5% chance that you're rejecting null hypothesis when it should have been accepted. So what if you are going multiple tests for a single experiment? So you are making 5% error in each of these experiments, and these 5% errors, they are going to add up because you're doing multiple tests for a single experiment. So it means that you're increasing your chances of making a type 1 error. So as the number of tests are increasing, the chances of making an error are increasing. For example, if you have performed only one test, your chance of error is 5%. And if you have performed 2 tests, then the chance of making an error is 10%. And if you have performed 3 tests for a single experiment, then the chance of making a type 1 error is 15%. So it means that the chances of making type 1 error are increasing as the number of tests in a single analysis, in a single experiment, are increasing. So we are increasing the chances of making type 1 error. So are we left at the mercy of the type 1 error, that we are going to make type 1 errors as the number of the multiple tests are increasing? No, there is a way to correct the type 1 errors. And how these type 1 errors, they can be corrected? By setting the level of significance to a more stringent level. For example, the alpha level of 0.01 or 1%. So in this case, you are going to reject your null hypothesis only if the probability of rejecting null hypothesis is 0.01, right? The probability of accepting null hypothesis is less than 0.01, then in that case, you're going to reject your null hypothesis. So you're, instead of 5%, you are doing it at 1%. So this is certainly going to reduce the chances of making type 1 error. So these statistical corrections, they are usually done by dividing the level of significance by the number of multiple comparisons that you perform. So if the number of the multiple tests that you're performing is 10 and your alpha level, which is usually the default level, which is 0.05. So 0.05 divided by 10 is 0.005. So this is your new level of significance. Now you're going to reject the null hypothesis at 0.005 level instead of 0.05. And if you have the 5 number of tests to perform, then it is going to be 0.01. So 0.05 divided by 5 is 0.01. So in this case, the probability of null hypothesis to be true or to be rejected is decided at the significance level of 0.01, which is 99%. So how this is going to create the difference? So in the single test, when you're performing a single test, your level of significance is 0.05. Your alpha level is 0.05, which means that you're rejecting null hypothesis if probability of accepting null hypothesis is less than 0.05, right? So this is what we usually do. But in this case, after the statistical corrections, what we are doing is that we reject null hypothesis if probability of accepting null hypothesis is less than the corrected level of significance, that is 0.01 or 0.005, etc. So instead of rejecting the null hypothesis at 0.05, we are rejecting it at 0.01 or 0.005. So is this going to solve our issue? That are we going to reduce the chances of making type 1 error? Yes, we are certainly going to reduce the chances of making type 1 error, because in this case the error rate is reduced. So in a single test the error rate is 5%, and after correction we have 1% or 0.5% or any other level which is decided after the new correction, right? So are we going to have our problem solved here or no? So apparently it looks that our problem is solved. But correcting type 1 error should be dealt with caution. Why? Because correcting the type 1 error increases the chances of making a type 2 error. Now, what is this? What is a type 2 error? Type 2 error is a false negative result, which means failing to reject null hypothesis when it should be rejected, right? Failing to reject null hypothesis when it should be rejected. And when this happens when you have your alpha level very low. So if the level of significance is set too low, then chances of failing to reject null hypothesis increase, right? Because if we were rejecting the null hypothesis at 5%, but now we are rejecting the null hypothesis at 1%, so it means that the chances of rejecting null hypothesis when it actually should have been rejected are becoming low. So we are going to increase the chances of making type 2 error. So we are left in a confusion. What should be done? If we are setting the level of significance at 0.05, then we are increasing the chances of making a type 1 error in multiple testing. But if we want to correct the level of significance for multiple testing, and we are correcting it by lowering the level of confidence or the level of significance, then we are increasing the chances of making type 2 error. So this is really a confusing situation, and what should we do in this case? So ANOVA is here to help us. So ANOVA overcomes these difficulties. So ANOVA means the analysis of variance, and this ANOVA is a single test, and this is done at the level of significance 0.05, which is the usual level of significance. So in a single test we are allowed to do comparison of multiple groups, right? So previously the multiple testing was required because the t-test allowed only 2 samples to be tested simultaneously. But here we can compare more than 2 samples in a single test. So because we are performing a single test, so we have a single null hypothesis, and we are going to reject or accept the null hypothesis at 0.05, which is the default level, or which is the accepted level of significance. And because we are doing single test, we are not doing multiple test, so we are not increasing the chances of making a type 1 error in this case. Now, what are the requirements of ANOVA? The observations, they should have a near normal distribution. There should be homogeneity of variances, because if we are comparing the population means, then population variances, they should be homogeneous. And there should be a continuous response variable. It means that the variable for which we are testing, that variable should be a continuous variable which is measured on the ratio or the interval scale, right? So it should be a continuous variable. Now I have used the term the response variable. What does that mean? That what is meant by response variable? Are we going to have different types of variables in ANOVA or no? So let's see what types of variables we have in ANOVA. So we have basically 2 different types of the variables in ANOVA. The first one is the nominal variable, which is also known as the independent variable, and this is also known as factors, and this is also known as the predictor variable. So these are the different names for the nominal variable that we have in ANOVA. And then the other type of the variable that we have in ANOVA is the measurement variable, and this is also known as the dependent variable or the response variable, right? So we have these two types of the variables in ANOVA. Nominal variable has different categories which are called samples or groups. In t-test, we have only two categories of the normal variable or the number of samples, right? So in the t-test, we only have two categories of the nominal variable, but in ANOVA, we can have more than two categories of the nominal variable or the number of samples. The measurement variable is going to be only one in ANOVA. Now let's understand the difference between these two variables through some examples and the difference between ANOVA and the t-test. So the state of affairs is the comparison of mean length of silver carps from different ponds, right? So this is our state of affairs. Now we are discussing two scenarios related to this. So the first scenario is comparison between mean length of silver carps from two ponds. And the scenario number 2 is the comparison between mean length of silver carps from 3 ponds. And we are going to define the variables in these two scenarios. So the first scenario is where we can apply the t-test because there are only two samples. So the nominal variable in this case is the location, which are the ponds, right? And how many categories do we have? We have two categories or samples, pond number 1 and pond number 2. And what is the measurement variable in this case? The measurement variable is the length. And how many measurement variables are there? This is only one, only length. Then in scenario 2, which is of ANOVA, because we have more than two samples, and the nominal variable in this case is location, which are ponds. And how many categories of the nominal variable do we have? We have three categories or samples, pond 1, pond 2, and pond 3. And how many measurement variables we have? We have only one, which is length, right? Now we have another example, and the state of affairs is the comparison of dry weight of leaves from different fields. We have two scenarios. Scenario 1 is comparison between dry weight of leaves from two fields, and the scenario 2 is comparison between dry weight of leaves from 4 fields. So for the first scenario, we can apply a t-test for the independent means, and in this case the nominal variable is the location or fields. And how many categories of the nominal variable do we have? We have two categories or samples, field 1 and field 2. And what is our measurement variable? The measurement variable is the dry weight of leaves, and we have only one measurement variable. Now in scenario 2, we have ANOVA, and the nominal variable in this case is location, which are fields. And how many categories do we have? We have 4 categories or samples, field 1, field 2, field 3, and field 4. And what is the measurement variable? The measurement variable is the dry weight of leaves. And how many measurement variables? Only one. Then we have another example, which is crop yield from different fields treated with different amounts of fertilizer. So we have two scenarios. Scenario 1 is comparison between crop yield from two fields with different amounts of fertilizer. We have scenario 2 where there is comparison between crop yield from 3 fields with different amounts of fertilizer. So for the first scenario, we have t-test. The nominal variable is the amount of fertilizer. So we have two categories or samples. The samples which received 50 kilograms per hectare, and the samples which received 100 kilograms per hectare of the fertilizer, right? So in this case, we have two fields. One field has got 50 kilograms per hectare, and the other field has got 100 kilograms per hectare. And the measurement variable or the response variable is crop yield. And how many measurement or the response variables do we have? We have only one. Then in scenario 2, the nominal variable is the amount of fertilizer, and we have three categories or samples. Field number 1, in which we have 50 kilograms per hectare fertilizer, and then the sample number 2, in which we have 100 kilograms per hectare of the fertilizer, and then sample number 3, in which we have 150 kilograms per hectare of the fertilizer. And the measurement variable or the response variable is only one, which is crop yield. As I said that there are different types of the ANOVA, so now we are going to discuss those types, and we are starting from the simplest type of the ANOVA, which is known as one-way ANOVA, or the one-way analysis of variance. Now, one-way ANOVA allows the comparison of any number of samples in a single test, right? So we are performing a single test of ANOVA, and we can compare the mean values of any given number of samples in that single test. And we can do that test to see the effects of a single independent or nominal variable. So this is the point to consider here, that in case of one-way ANOVA, we are going to see the effects of only a single type of the independent or the nominal variable or the predictor variable. And this ANOVA is also known as one-factor ANOVA, single-factor ANOVA, or single classification ANOVA. So these are different names for one-way ANOVA. So in one-way ANOVA, we have one measurement variable and one nominal variable. So in one-way ANOVA, we are going to have only one nominal variable. We are going to have different categories of that one nominal variable, and we are going to have one measurement variable against which we have multiple number of observations. So we have multiple observations of the measurement variable taken for each value or category of the nominal variable, right? So the type of the nominal variable is 1, and the number of categories of the nominal variable, they could be from 3 to many. And the measurement variable is only 1, and there are multiple observations of the same measurement variable in each category of the nominal variable. Now the other type of the ANOVA is a two-way ANOVA. So two-way ANOVA allows to see the effect of two conditions or two independent variables in a single comparison. Now in contrast to one-way ANOVA, in this ANOVA we have two nominal variables. We have two types of the nominal or the predictor variables, and we can see the effects of these two conditions in a single test. So we have one measurement variable and two nominal variables. This is also known as the two-factor ANOVA or the factorial ANOVA. For example, if we wish to compare the mean lengths of the silver carp, or if we want to compare the mean length of the 3 races of the species from 3 different islands, as we saw in the first slide. So in that case, if we want to see the effect of their sex as well, right? So we want to compare the mean values by sex and by island of origin. So in this case, we have two nominal variables, the island of origin and the sex. And if we want to see the effects of both of these conditions in a single test, again, we're talking about a single test. We're not talking about multiple comparisons, right? So we are allowed to do that. So in ANOVA, we have this flexibility that we can have more than one type of the nominal variable, and we can have more than 3 categories of each of these nominal variables. So that is why ANOVA is so widely used, that it has the flexibility of having any given number of the nominal variables and any given number of the categories in each of these nominal variables. And all of these effects, they can be assessed through a single analysis, through a single test. So we are not committing type 1 error in this case. And this also allows us to see the interaction effect. So this is not enough that we are going to see the individual effects of the two nominal variables, like we are seeing the differences in the mean values by their sex and by the island of origin at the same time. We can also see the interaction effect of these two different nominal variables, right? So this is an added advantage of using a single test, that you are not just calculating the effect of the two nominal variables on a single measurement variable, on a single outcome or the response variable, you are also seeing the interaction of these two nominal variables with each other, that what is their combined effect, what is their interactive effect on the measurement variable. So this is the two-way ANOVA. Then we have n-way ANOVA. We can have three-way treatments, we can have four-way treatments, and so on. So we can have any number of the nominal variables, any number of the treatments, and we can see their effects simultaneously in a single test, in a single ANOVA. So this is a multiple-way ANOVA or the n-way ANOVA. For example, if you want to compare the heights of individuals, right? So we can simultaneously see the differences in the height of individuals by their location, by their gender, by their nutritional status, and by their ethnicity, all at the same time in a single test with a single level of significance, 0.05, right? So this is n-way ANOVA. This could be three-way ANOVA, this could be four-way ANOVA, and so on, depending on the number of nominal variables that we are going to check. Now let's have a quick comparison of these three types of ANOVA. So what are their different names? The one-way ANOVA is also known as the one-factor ANOVA, single-factor ANOVA, single classification ANOVA. The two-way ANOVA is also known as two-factor ANOVA or the factorial ANOVA. The n-way ANOVA is also known as the multiple-factor ANOVA or factorial ANOVA. So these are different names. And then the number of nominal or independent variables or factors or the predictor variables. So in one-way ANOVA we have only one, right? We have only one type of the nominal variable. It can have categories of 3 or more, but the type of the nominal variable is only one. In the two-way ANOVA we have two types of the nominal variables, and their categories could be more than 3 in each of these nominal variables, but the types of the nominal variables are 2. And in case of n-way ANOVA, the types of the nominal variables are 3 or more. Then the number of categories of the nominal variables in one-way ANOVA, it could be 3 or more. In two-way ANOVA, for each of the nominal variables, it could be 3 or more. And in n-way ANOVA, for each of the nominal variables, it could be 3 or more. Then the interaction effect of the nominal variables, because we have only one nominal variable, so there is no point in checking the interaction because there is no other nominal variable. But in two-way ANOVA and the n-way ANOVA, we can have their interaction effect also calculated. So we can see the interaction effects of the nominal variables in two-way and n-way ANOVA. And then the number of measurement or the dependent or the response variable, this is only one. In all of these cases, this is only one. So this is a quick comparison of these three types of the ANOVA. Now let's see the difference between one-way and two-way ANOVA with examples. So the state of affairs is comparison of mean length of silver carps. So we have scenario 1 in which there is a comparison between mean length of silver carps from 3 ponds. So for that purpose we are going to use one-way ANOVA. So the nominal variable in this case is the location, which are ponds, and the number of categories of the nominal variables are 3. So there are 3 categories of location: pond 1, pond 2, and pond 3. And the measurement variable is only one, which is length. Now scenario number 2 is the comparison between mean length of female and male silver carps from 3 ponds. So in this case we are going to use two-way ANOVA. Why? Because we have 2 nominal variables. One nominal variable is their location, which are different ponds, and the other nominal variable is sex. So we have 3 categories of location: pond 1, pond 2, and pond 3, and we have 2 categories of sex: female and male. And the measurement variable is only one, which is length. So in this case we are going to see the mean difference between the length of the silver carps by their location and by their sex, and we can also see the interaction effect of these 2 variables. Then the next example is the comparison of dry weight of leaves. So the first scenario is comparison between dry weight of leaves from 4 fields. So we are going to apply one-way ANOVA. Why we cannot apply t-test here? Because there are more than 2 categories of the nominal variable. So here are 4 categories, and what is the nominal variable? It is location, which are different fields. So there are 4 categories of location: field 1, field 2, field 3, and field 4. And the measurement variable is only one, which is the dry weight of leaves. Then in the scenario 2, we have the comparison between dry weight of leaves from 4 fields in 2 seasons, right? And we are going to apply the two-way ANOVA because the number of nominal variables are 2, location and seasons. So there are 4 categories of location: field 1, field 2, field 3, and field 4. And there are 2 categories of seasons: fall and spring, for example. And the measurement variable is only one, which is the dry weight of leaves, right? So this is another way to compare the one-way ANOVA and the two-way ANOVA. See another example, which is the comparison of crop yield. So scenario 1 is comparison between crop yield from different types of fields with 3 different amounts of fertilizer. So in one-way ANOVA, the nominal variable is only 1, which is the amount of fertilizer, and the number of categories of the nominal variable are 3. The 3 categories of the amount of fertilizer: the amount of fertilizer, which is 50 kilograms per hectare, and those fields which have the amount of fertilizer as 100 kilograms per hectare and 200 kilograms per hectare. So these are 3 categories. So we are going to apply one-way ANOVA, and the measurement variable is only one, which is crop yield. Then in scenario 2, we want to have a comparison between crop yield from different fields with 3 different amounts of fertilizers and 3 different types of soil. So because we have 2 types of the nominal variables, so we are going to apply two-way ANOVA. And what are these 2 nominal variables? Number 1 is the amount of fertilizer, and the other one is the type of soil, right? So these are the 2 predictor variables, or the 2 nominal variables. And there are 3 categories of the amount of fertilizer: 50 kilograms per hectare, 100 kilograms per hectare, and 200 kilograms per hectare. And we have 3 categories of soil: loamy soil, clay soil, and chalky soil, right? So we are going to apply two-way ANOVA in this case because there are 2 nominal variables. And the measurement variable is only one, which is crop yield, and this is also our response variable. So I think the difference between the one-way ANOVA and the two-way ANOVA is clear.